All right, hello everyone. Welcome to exam 5 review. It feels like we have an exam every single week, and we kind of do, but it's every other week. So at least we get a week between to not relax, but recuperate maybe. But all right. So chapter or exam 5 is all about chapter 10 and chapter 11. Chapter 10 is about radical reactions and chapter 11 is about synthesis, or module 10, module 11, however you want to say it. So to be honest, we'll be going over most topics from chapter 10 today, and then we aren't really going to go over any specific topic in module 11 because in my opinion, this synthesis chapter, it's not really a how do you say this? It's not really a chapter of new material. It's a chapter of applying the material that you have in different ways. And I'll show you how it's where we'll break everything down, make it nice and simple, and try to keep things simple as possible for you guys to understand. All right. So again, for the topics, I will be going over the exam 5 topics email he sent us. So we can see here that module 10 has homolytic cleavage, alkanes halogenation, allylic bromination, radical addition, free radical polymerization, etc., etc. All of those topics seem very, very scary, but we are going to break them down into baby words so we can all understand them because your brains are probably tired. Somebody said, can we find your videos from the last exam on YouTube? Uh, yes. All of my previous exam reviews are still up there. They should stay up there. I don't intend to take them down, at least not anytime soon. And definitely not until the semester is over if I can help it. But yeah, any exam reviews, anything that I do with you guys should end up on YouTube and it should be staying there as far as I know. All right? Okay, so are there any other sort of preliminary questions before we get started here? If not, then I will just go into it. All right, so chapter 10 is all about radicals. Up until this point, we've been doing sort of, I don't know, we've been doing ionic equations. And the only reason I'm sort of hesitant to say ionic equation is sometimes you guys may think of ionic bonds, such as a metal versus a nonmetal, but that's not what I'm talking about. We're still talking about covalent bonds. We're just forming ions when we do an ionic equation with those covalent bonds. So let's compare, or let's just look at those covalent bonds that we've been looking at for this entire chapter. So an example of this would be, what if I have a chlorine leaving group? What'll happen here? We are going to do something called heterolytic cleavage, and I'll write that down. Heterolytic cleavage. So what heterolytic means, it means all of the electrons in all of the covalent bond will either go to one atom or another. So it would go all to A or all to B, in this case all to B. And then when we did our leaving group here, it all went to the leaving group and we ended up with A plus and B minus. We ended up with Cl minus, and then our carbocation. So we can see here why this is an ionic equation, because we have full ions that we're working with. When we talk about radical equations, we'll be doing something a little bit different. So let's say that we have these here. When we do radical equations, we are going to do something called homolytic cleavage, which means the same. So I keep spelling this wrong, homolytic. You'll have to forgive me, I'm not an English major. Uh, Homolytic cleavage. And so essentially what this means is that half of the covalent bond will go to one atom, and then half of the covalent bond will go to another atom. So in the case for A and B, half of the electrons will go to B, half of the electrons will go to A. You can see here, if we pause, we can see I'm using a sort of different type of arrow. Whenever we do heterolytic cleavage, we're representing a full pair of electrons. What this means is this arrow over here is carrying two electrons. And you can sort of see that in its sort of two little pockets here. But when we're doing homolytic cleavage, we can see that these arrows can only hold one electron. We can see it only has one pocket. And that's how I sort of remember things. A double-headed arrow shows the movement of a full pair of electrons because it has two pockets, and a single-headed arrow shows the movement of a single electron because it only has one pocket. You may also see this referred to as like a fishhook arrow because it kind of looks like a fish hook that a fish would take a bite out of, like that. But I usually call them half-headed arrows, but fish hook arrows are exactly the same thing. And so when we represent this with a bromine here, we'd see arrows like this. And so then what happens is we end up with two radicals. And so these radicals, we don't sort of consider them to be, we don't consider them to have full charges, is what I mean here. So that's why we show them with a single electron as well as the rest of their electron pairs, but we don't give them a full charge. Still, we kind of consider these sort of in between electron deficient and electron rich. I consider them in my brain to be electron rich because whenever we end up drawing arrows with them, the arrows are going to go from the single electron. I know it's kind of a silly way to remember it, but I always remember, okay, so half of the arrow has to come from the bromine, half of the arrow has to come from the radical, and we will see that implemented later. I'm just showing you first off the difference between an ionic heterolytic cleavage and a radical homolytic cleavage. So up until this point, again, we've been doing heterolytic cleavage, and now we're going to dive into homolytic cleavage. So let's talk a little bit about radicals as a whole very, very quickly. So let's compare, oops, that is red, that is not black. Let's compare let's compare radicals to carbon ions. So let's say that we have carbocations. Sorry, I'm mixing up all my words today. So we can have a primary carbocation and a primary radical, a secondary carbocation and a secondary radical. We can have a tertiary carbocation and we can have a tertiary radical. And finally, you may have heard this before when we talked about carbocations as a whole, but just to jog your memory, we can also have something called an allylic carbocation. And in the same vein, we can also have something called an allylic radical. And so the stabilities of these things are going to follow the same trend. These ones down here are going to be the most stable, and these ones up here are going to be the least stable. So if I drew an arrow right here, we can see the difference. Let me quickly show you why allylic carbocations and allylic radicals are so stable. Allylic anions, carbon anions, would also be very stable, and I will also show you why here. So we have a carbocation, a carbon radical, and a carbon anion. All right. So because of that double bond present, we can create a new resonance structure. And if you remember, the more resonance structures that you have, the more stable you are. So for example, this one up here would show its resonance structure, sort of swinging the double bond over between these two carbons and away from this carbon, thus forcing the positive charge onto the other carbon. You see here, this arrow right here, I don't know if I pointed this out when we talked about resonance structures, but this double-headed arrow here, this is specifically used for resonance structures. I just wanted to point that out very quickly, just in case that wasn't clear before. So if we look at carbon ions, so I'm going to skip the radical really quickly, we can do the same sort of thing, just slightly different. So we can't exactly do what we did before where we swung the double bond around, because this carbonyl already has 8 electrons. So instead of doing that, what we will do is we'll use these electrons here to create a new double bond. But again, this carbon cannot have more than 4 bonds. So that means that it forces the other bond to go off, and that sort of moves that negative charge over to the other carbon as well. You can see here we have the same sort of resonance structure. And again, we're going to do the same type of thing with our radical allylic carbon. The biggest difference here is we're going to be using a lot of half-headed arrows, because you can see here that the radical sort of falls between both the carbocation and the carbanion. So what it's going to do, it's going to borrow half its arrows from each of them. So one half of the arrow will go from that one electron to create a new double bond. And then this double bond over here is going to sort of contribute one of its electrons to form a new double bond. That leaves one final electron in this double bond here, which then will go onto that opposite carbon, and thus we will get this resonance structure right here. All right, so that's sort of the rundown on allylic carbocations, allylic radicals, and allylic anions. We can see here they all act in a very similar way, but just as a heads up, we will be focusing a lot more on the radical allylic carbon rather than the carbocation or the carbanion. I just drew them here to sort of show you what's going on with these, just to show you the differences between the carbocation, the radical, and the carbanion. All right. Does anybody have any questions about that? If not, then we will continue on. All right. And I know that in his class, Dr. Dowdy really likes to go with bond dissociation energy, or BDE. And I don't know about you, but I always think of something else when I see those letters. But anyways, when we're talking about bond dissociation energy, we're actually going to be talking about which one is going to make the most stable sort of either carbocation or radical. So if we compare sort of a primary carbon-hydrogen bond right here, right there, and we compare it to uh, a allylic carbon right here, we can see here, oh, if I take away that hydrogen there, I will end up with a primary radical. If I take away that hydrogen right here, I end up with an allylic radical. So that means that the allylic radical will be oops, that is not what I meant to do. The allylic radical is going to be far more stable than the primary radical. So what this means is that it's going to take less energy to break that bond. So that means that this is going to have a smaller bond dissociation energy. It's written in the PowerPoint that this in particular would take 364 kilojoules per mole to break, whereas a primary, this one here, would take about 410 kilojoules per mole to break. So we can see here that if we create a more stable sort of intermediate, whether it be a radical intermediate or a carbocation intermediate, the bond dissociation energy goes down, because it's easier to break that bond because it will form a more stable intermediate. So that's sort of the rundown of the stability of free radicals and sort of the relationship between bond dissociation energy and sort of the radical stability. So this will kind of come into play when we're talking about the delta H of reactions. So for example, this reaction right here, going from this guy here to another radical, is going to have a higher delta H than this one here. Because again, we're going to have to put in more energy to break that bond than this one here. So that means that our delta H for this one will be higher than the delta H for this one over here. All right. One last thing, talking about stabilities. Let's talk about the stabilities of different allylic radicals. So let's say that I have a double bond right here, and there are two places that I can put a radical on or put a single electron on in order to make it an allylic allylic radical. Sorry, I keep trying to say allylic carbocation because in Orgo 2, you'll be dealing with those quite a bit. Uh, So somebody said you want a smaller bond dissociation energy. Generally, yes. The smaller bond dissociation energy means you're making a more stable intermediate. So let's look at here. So there's allylic 1. That would be the same thing as this one up here if we put our radical in there. And then here's radical number 2 over here. And let's sort of show both of these. So here's the red one. If we end up with this here, we'll put our radical here. And our resonance structure would look like this. So we can see here that we have a primary allylic radical and a secondary allylic radical for both of those resonance structures. If we put the radical on the green carbon, we would end up with this guy here plus this resonance structure here. So you can see here we have a primary radical, just like the first one, but now we have a tertiary radical. So now we can see here the difference between these two radicals is their stability. So the green radical is going to be more preferred than the red one because overall it'll create more stable radicals in that it creates a tertiary allylic radical compared to this secondary allylic radical. So that's also something you kind of have to look out for when we're talking about allylic radicals. All right? Okay. So we talked about free radical formation, the delta H of radicals, stability of free radicals, and so now we're going to talk about the overall reaction of a radical. Somebody said the red product will be present, but just minor, right? Yes, this one would still be present, but again, we're going to talk about major and minor products in a little bit when we talk about bromination versus chlorination and the such. But yes, as a general rule, the red product would be less abundant than the green one because the green creates more stable transition, not transition, but intermediates. All right? Okay. So let's talk about the general reactions of radicals. There are a few different ways that radicals can react. So of course, the first step is to form a radical, and we'll talk about each of these steps in a little bit. But let's just say that we have a radical right here, and we're going to call it just X, our X radical. And so they can either react with sigma bonds, so single bonds. So if we have R connected to a hydrogen, or they can react with double bonds. So if we have R double bonded, or let me just do a regular carbon here, a carbon double bonded to a carbon, or they can react with other things. They can react with themselves, with other radicals. So like if I have another X radical X radical right here, whew, it's a mouthful, that can also react with themselves. So let's go over each one of these different reactions here. So the first one is the reaction with a regular sigma bond. What will happen is this radical is going to want to form a bond. And then the hydrogen is going to say, oh, I'm pretty attracted to this guy because he has kind of a negative charge. And hydrogens love negative charges. So it's going to want to go and meet it in the middle. And again, bonds only are composed of 2 electrons. So the hydrogen only needs to contribute one of its electrons. That forces this bond to break homolytically and then force that R group, our alkyl group, to become an R radical. All right, so essentially what we did here is we kind of transferred the radical and created a new sigma bond. All right, now when we talk about double bonds, what we do is, oh, this double bond is going to want to form a bond with this one right here because, again, it can either act as an electron deficient or electron rich. And so, again, this guy here is going to have some electrons to share with that other radical. As a result, they're going to make a new bond. But again, each bond has to have 2 electrons. So this electron has to come over here and then go on this carbon right here, thus breaking the double bond, but there's still a sigma bond present, as well as an X bond right here, and now we've moved the radical onto a carbon. Finally, The last type of reaction, I guess you can say, is the reaction of a radical with another radical. What this does is this radical says, hey, you need an electron. This radical says, yeah, you also need an electron, so I'll share mine. And so what they do is they create a new bond with each other, and there's no more radicals left. All right? So here are the three main different reactions that we can kind of do with radicals, like once we have them. All right. Does anybody have any questions about this? If not, then we will go over the overall mechanism. All right, so let me clear this. So the overall mechanism of radical reactions tends to have 3 steps. Oh, somebody said, do we have to know initiation, propagation, and termination? That's what I'm about to go over right now. So again, 3 steps, I kind of spoiled them for you, but the first step is going to be initiation. Hold on, do I know how to spell initiation? Initiation, I think that's right. Then there's propagation, and finally, termination. Again, I don't know how to spell. What do you take me for? Somebody who writes papers? No, I just do chemistry. Anyways, so the way to tell if something's initiation, propagation, or termination, I've always said, is to look at how many radicals you have on each side of the reaction. So for initiation, you start with 0 radicals, and then you end up with 2 radicals. For propagation, you start with 1 radical, and you end with 1 radical. For termination, you start with 2 radicals, and you end with 0 radicals. All right? So this is sort of a rule of thumb to determine which step we are doing. So let's do an example of initiation. So we could have Cl attached to a Cl. And just as a little hint here, whenever we're doing any sort of radical reaction, we are going to have to introduce either light, Hv, heat, or something known as ROOR. And we will cover this in a little bit, but the idea here is we're giving in energy to sort of overcome that bond dissociation energy in order to force these to homolytically cleave. So we are going to cleave these in half. We start with 0 radicals, we introduce energy, and we create 2 chlorine radicals. I'm not going to draw the rest of the electrons because I'm lazy. I hope you'll forgive me. So the next step is going to be propagation. Now, propagation can go on for multiple steps at a time. You could have 1 propagation step to make a new radical. That radical can go on to do another propagation step and then create a new radical, which then can go on to another propagation step, and so on and so on. That's why it's called propagation, because it's self-propagating. It can just keep going on forever until it comes into contact with another radical. So let's quickly do an example or 2 examples of propagation. So we could have the reaction with a sigma bond, like we saw before. So let me erase this. So the reaction with a sigma bond, that would be, we'll have our chlorine right here. Just like before, we're going to homolytically cleave to create a new hydrogen-chlorine bond. And then we create a new carbon radical. So you can see here that we started with a chlorine radical and we ended with 1 carbon radical. We started with 1 radical, we ended with 1 radical. This is going to be propagation. Another example of propagation may be, you're not going to see chlorine doing this very often. You're more likely to see bromine doing this, but I'm just going to do it with chlorine just to keep things consistent. But you can see it done with a double bond here, where the double bond sort of meets chlorine in the middle, and then the other electron from that double bond goes onto the other carbon, and we end up with a new chlorine bond right here and a new radical right here. Again, you're still starting with 1 radical and you're still ending with 1 radical. The reason why I circled ROR is because I'm going to come back to it later, because it's slightly different from light and heat. All right. So, so those are two examples of propagation. And so now I'm going to give you a few examples of termination. Again, we're going to start with two radicals. We could start with this radical right here plus one of those chlorine radicals. Oh my goodness, I went ahead and drew the electrons. Anyways, and what'll happen here is oh, I'm sorry, my doorbell went off. I wonder if you could hear that. Each one of the single electrons here will meet in the middle and they will create a new sigma bond. And so we started with two radicals and we end with zero radicals. All right. Another example would be if we had two chlorine radicals interacting with each other and sort of negating this whole reaction overall. We'll have them meeting in the middle and we end up with ClCl. So both of these are termination. Both of these are propagation. They're just sort of different types of termination and propagation. That's why I'm going to advise you to count the radicals you begin with and the radicals you end with in order to the radicals that you begin with, the radicals that you end with, in order to determine if it's initiation, propagation, or termination. Sorry, I got distracted because I read the chat. It says, can you also place that chlorine on the allylic position as another product? Yes, I'm just showing you examples because remember, back before we talked a little bit about the reaction of radicals, just overall. We talked about the reaction with a sigma bond, the reaction with a pi bond being a double bond, and the reaction with another radical. And you can see here that we've done one of each of those, and I just wanted to showcase each of those. Somebody said, are there any other termination products? I think so. Honestly, as far as termination goes, whatever radicals you end up with propagation, oops, I accidentally paused my screen share. Whatever reaction or whatever sort of propagation radicals you make, you can make those into termination radicals. So like, for example, I can react two of these together and create a new carbon-carbon bond. It's just sort of what the question is asking for specifically, because the final product, the termination product, is determined by what reactants that you're using as a general rule. All right. Does anybody have any questions about that? If not, then I will
So,
continue on. Oh,
sorry. So does propagation or termination like give you the end products of a reaction?
termination does.
Termination does? Okay, because I've been hearing like conflicting answers.
Well, the thing is okay. So the difference between propagation and termination, propagation, that can possibly give you an end product. I'm totally going to say yes, that can give you an end product, but that's not the end of the reaction as a whole. The end of the reaction as the whole will be the termination. But when you could make your final product, like the product that you want, in the propagation step, it just depends on what you're doing. Does that make sense?
Yeah, thank you.
And in propagation, can the arrow for the double bond go on the right side instead? Yes, I just sort of arbitrarily chose which carbon to put which on. All right. Okay. So, um, let's see. So we talked about common reactions of radicals. So now, let's talk about radical initiators and inhibitors. So, when we talked about before, like uh, light, HV light, delta heat, or ROOR. These are all technically initiators, but this is going to be sort of a special initiator because this is going to undergo something called auto-oxidation. What this means is we're going to have RO connected to OR just in the middle. And then spontaneously, what's going to happen, these are kind of going to degrade through homolytic cleavage into two OR radicals. I'm going to sneeze. Oh gosh, I just said I'm going to sneeze and now I'm not going to sneeze. But you can see here that this spontaneously undergoes that homolytic cleavage, and we did not need to put in light or heat for that to happen. This happens a lot in our bodies. And this is what creates something called reactive oxygen species, ROS. And that's why that's why a bunch of health people say to eat a lot of antioxidants, and that's to get rid of these reactive oxygen species. However, in our case, we can use these reactive oxygen species to form radicals from stuff like Br2, because we can sort of treat this as sort of a semi-propagation step. This whole process here will be under the initiation umbrella, but we're kind of going to do an oxidation reaction. I'm not an oxidation, but a propagation reaction, in that we're going to start with one radical here. We're going to end with one radical here. So while this second step right here, while this does look like it should be just a propagation step, all of this is going to be considered the initiation step, because ROOR, breaking apart, is sort of considered to be sort of our light or our heat that starts out the reaction and not in itself part of the reaction. Does that make sense to everybody? I hope it does, because that can be pretty confusing, I know. But that's the idea sort of behind auto oxidation and how we use ROOR. So all of this is initiation. Yes, exactly. And so to form these ROOR species is part of that auto-oxidation process. So what you'll see is an R attached to a hydrogen plus O2. And what will happen is that oxygen will kind of, that O2, those will kind of break apart to form radicals in of themselves. And then they'll combine with the hydrogen in the R group right here to make our R. In this case, our second R is going to be H. And so we can see how those species are made. And auto-oxidation sort of happens all the time in our body to create these ROOHs in order to sort of use them in our bodies for fatty acids, through the Krebs cycle, all of that stuff. Again, you don't need to worry about the sort of biology portion until you get into stuff like biochemistry or molecular biology, but you do need to know sort of the process here. All right? Get rid of the microbes. Exactly. So the reason why we need to know this auto-oxidation is because we need to know how to form this specific initiator right here, being ROOR, where those R's are either R groups, like actual alkyl groups, or hydrogens. Okay? So just know that if you combine sort of like an R group here, RH, with O2, that'll spontaneously form ROOH, because these here, these will sort of break apart and form radicals all by themselves. That's why it's called auto oxidation, because auto means self. Okay. So again, let me remind you, the initiators for radical reactions are either going to be light, known as HV, heat, known as delta, or ROOR. So we've talked about initiators, but what about inhibitors? So let's talk about hydroquinone. So auto-oxidation ends with hydrogen abstraction to get ROOH. Yes, ROOR is ROOH. Like, these R groups can either be actual carbon groups or they can be hydrogens. So, like for example, if I had R attached to R, that technically could also interact with O2 in order to make ROOR. But we more often than not see this second R being hydrogen itself. And those R groups sort of represent either carbons or hydrogens. So ROH and O2 can create either ROOR or ROOH. Um, it would just be this one here. RH plus O2 creates ROOH. And that's sort of the idea behind autooxidation. Did that answer your question? No problem. Okay. So back to radical inhibitors. So one good example of a radical inhibitor is hydroquinone. I think that one is pretty famous right now. But essentially what will happen is one of these oxygens on these hydrogens, or one of these oxygens in these OH groups, they'll be extremely happy to accept a radical. Why? Because this is basically an allylic radical on steroids. So basically, we'll be able to do just a bunch of different resonance structures all around this whole sort of central benzene ring. And so because of all of that resonance, it's able to hold on to radicals really, really well. As a result, it'll sort of mop up all of the radicals in a certain radical reaction. So, for example, if you're doing a radical reaction in lab and you want to stop that reaction, you don't want any more radicals, then you would probably introduce something like hydroquinone, anything that's really, really resonance stabilized uh, with a radical on it, and that will stop your radical reaction. Somebody said, how would we see it written out on the exam? I'm not 100% sure. You may be asked to select the radical inhibitor, but I don't see the exam, so I cannot tell you what's on it. And even if I did see the exam, I couldn't tell you what was on it. And I'm not 100% sure how everything's going to be written out. Uh, I'll repeat that. I don't know what's going to be on the exam. I don't see it. And even if I did see it, I wouldn't be allowed to tell you. So I can't tell you exactly. Oh, somebody said, what exactly is inhibiting it? Okay, I understand your question now. So this inhibitor, it's kind of inhibiting the reaction from going forward because it sucks up all of the radicals. Because it has so many resonance structures, it's super, super, super stable with a radical. And as a result, it will very easily form this radical, which then can sort of be passed around all the way around our structure here. And then if we end up creating a radical on this oxygen as well, basically what can happen is we can move the radical over here, uh, right here, double bond here, double bond here, double bond here. The next resonance structure would just combine these two radicals into oxygen double bonds here and here. So we can see here that with a radical with that radical there, that gives a lot of resonance and thus sort of stabilizes this whole thing. Somebody said, I heard that you shouldn't break benzene rings because the resonance is unstable when you break those rings. That is technically true, but we aren't breaking this benzene ring. We're breaking the oxygen-hydrogen bond. We're not really breaking any of the benzene ring. We're just adding more resonance levels to it. Somebody said, does this happen in the termination step? This step right here would be our termination step because we technically have, quote unquote, two radicals turning into zero radicals. They're just on the same carbon. This here, when we formed this radical, that would be a propagation step. This would just be a resonance structure. We wouldn't call that propagation, termination, or whatever. It's just resonance. Okay? Does that clear up the idea of radical inhibitors? I know that radical inhibitors are sort of a difficult concept, and on the PowerPoint, you'll see two inhibitors like drawn out that says traps radicals in aqueous environments and traps radicals in nonpolar environments. And I'll draw those two out just very quickly. So this one, just roughly, and then it has like a little arm over here that I'm not going to draw. This one will trap radicals in an aqueous environment because, again, it'll work very similar to that benzene ring structure that we saw before. When we add the radical right here, that will cause a resonance between these three oxygens here, essentially. And what's important to note about this guy here is that there is an abundance of oxygens. There's an abundance of polar bonds, and as a result, this guy can easily dissolve in aqueous environments. So, if we wanted to stop a radical reaction that was occurring in like a beaker full of water, then we would use this inhibitor. If, on the other hand, we wanted to inhibit a radical reaction that was happening in a beaker full of, I don't know, uh, hexane or cyclohexane, basically, we would have to use a structure that will trap radicals in a nonpolar environment, such as this one right here, which has like a really long carbon chain this way. We can see here. And again, we can see that I missed a ring right here. And this has an oxygen right here. But we can see here that when we take away the hydrogen here and we make this a radical right here, that's going to be stabilized by resonance once again. The biggest difference between these two is that this one has a lot of oxygens. And because it has a lot of oxygens, it has a lot of polarity. So it can be used in a polar aqueous environment. Whereas this one over here has not enough oxygens to compensate for the amount of carbons. And as a result, it won't work in an aqueous environment, but it will work in a non-polar organic environment. So that's why all of those are sort of shown on the screen, on the slide in the notes and everything, is because certain inhibitors, certain radical inhibitors, can only be used in certain situations because of their chemical makeup. All right? Does that make sense? Does that clear up any ideas about radical inhibitors that you may have had? Because I know this is sort of a complex topic and it can be quite confusing if it's not explained step by step for you. All right. Awesome. So, now we can finally get on to halogenation of alkanes, which is a lot of fun because up until this point, alkanes, we haven't been able to do any reactions with them. If we had something like this, we couldn't do any reactions with it. Think about it. Up until now, the only way we've been able to do any sort of reaction in this class is if we had an alkyl halide or if we had some kind of pi bond, be it a double bond or a triple bond. Well, this guy here has none of those things. So now what we can do is basically force this to become a radical, which then we can turn into an alkyl halide, which we then can do further reactions with, which is why this radical mechanism, this radical stuff is so important because now we can finally react with just regular old alkanes. All right? Okay. So again, so generally, halogenation is going to follow that initiation, propagation, termination step. So of course, step one, which is going to be the initiation, is going to be introducing light or heat or ROR. So I'm going to use HV here to those halogens in order to turn them into two halogen radicals. And again, I'm going to sort of skimp out on drawing all those electron pairs because I am very lazy. Um, anyways, so when we have this halogen right here, this halogen radical, then in the propagation step, essentially what we can do is one of those radicals can come in and create one of the carbons on our alkane chain to become a radical itself. Which carbon? It's going to depend on which halogen we are using and which radical will become more stable. And we'll talk about this in a little bit. So let's change up this alkane just very, very quickly. So now there are two possibilities for our halogen, or not our halogen, our radical intermediate. So there's this one where we create let me draw it, where we create a secondary halogen, or we could do a different propagation step where we create a primary a primary radical. Sorry, drawing takes a little bit of time. So of course, I know we talked about it earlier, how this first one with the more stable radical will be more stable, and we're generally going to prefer it. But sometimes this intermediate will be preferred. Why? Well, let me draw you some reaction diagrams. So we'll draw this one and we'll draw this one, and we're going to draw going from the reactants to the intermediates. All right? So there's this one here, there's this one here, and of course it will continue on to go on to the products, but we're not really worried about that right now. All right? All right, so we can see, we start here at the reactants, which I'll label with R, and then we end at our intermediates. That means our reaction isn't completely done. We're just focusing on this step right now. So what we're going to sort of zoom in and look at is this transition state right here. So do you guys remember something we talked about a little bit earlier about how whenever we have a transition state, it's going to resemble whichever product or reactant it's closer to. We talked about this a little bit before, and I think it's called something like the Hammond postulate. I cannot spell Hammond. The Hammond postulate. So because of the Hammond postulate, that can force one of these two different intermediates to be preferred. How? Well, let's look at our transition states. So for both of these. So if we look at the transition state for this one right here, we can see that it's sort of breaking right there, or it's going to be breaking right here. Okay, so now when we see this, we're going to say, all right, depending on if the transition state is closer to the reactants or the products, that's going to determine which one of these bonds is quote unquote more broken. Okay? So if it's closer to the reactants than the products, then this bond with the X is going to be way longer and it's going to be less stable. However, if we are closer to the intermediate, then this bond here is going to be way less than this bond right here. Is everybody with me so far? This is kind of an abstract thought process, and I don't want to sort of lose anybody. Okay, let me redraw this really quickly. So let's say that we're just looking at this first one right here. Let's say we're just looking at this first one. And this first graph right here, this transition state will be closer to the reactants. So that means this is going to resemble the reactants way more than this intermediate. As a result, the hydrogen bond will be very, very small. It'll be pretty strong still. And the hydrogen-chlorine bond will be a lot weaker. Okay? If we're down here and we're a lot closer to our intermediate that looks like this than our reactants that look like this, then that hydrogen bond is going to be a lot weaker. And that hydrogen-chlorine bond is going to be a lot stronger. All right? Does this make sense so far? Does anybody have any questions about this? So what is preferred? That's where the question lies. So when we are looking at this one in particular, obviously both of them are going to form because this will form the more stable radical. But if we look at that other with the primary, where, okay, so with this top one, it's going to be closer. With this bottom one, it's going to be farther away. We can use the same sort of ideas that we used before when we talked about transition states of, alkenes and how stable those are. We can see here that, oh, this is going to be like a partial radical, and this is also going to be a partial radical. This up here This is going to be a smaller partial radical. I'm trying to represent that with a smaller partial thing. This will be a smaller partial radical. Oops. A smaller partial radical. So, when we're looking at these, if we are doing this first transition state, it doesn't really matter which one we do. Because the transition states are so close to each other, the radical is so small, we're not going to mind too much. So when we're this first graph, we aren't going to really mind which radical we form because the transition states are basically going to be the same energy-wise. This happens in chlorination. However, when we look at this bottom graph, when our transition state is closer to the intermediates than the reactants, we can see that our radical is way bigger. And we can see that oh, I put chlorine for both of these. This one down here should be bromine. Anyways, we can see that that bigger radical is. So that bigger radical is going to highly prefer the one that's more stable. So that means it's going to prefer this one way more than this one because this with the intermediate closer to the intermediates is going to have a higher amount of a partial radical than this one here. As a result, when we do bromination, which has this graph, it's going to prefer the more stable radical over the less stable one because of the Hammond postulate. All right? Does that make sense to everybody now? Because this is a hard concept and I'm explaining it the best I can. Okay, awesome. I'm so glad I was able to explain this to everybody. So the transition state is what's ultimately going to decide which radicals we are going to form. So that means that when we do chlorination with the graph that looks like this, we're going to be able to form both types of radicals because the transition state doesn't differentiate between the two. Whereas when we do bromination, it has a much higher amount of a partial radical, which means that transition state is really going to push for the more stable transition state, aka the more stable radical. All right? Okay. All right. So what this means is that when we finish with the termination step, I'm kind of running out of room, but you'll get what I mean. When we finish up with the termination step, one of our products could look like this, and our other product looks like this. The amounts of each product is going to depend on whether we're doing chlorination or bromination, and I'm going to detail that in just a second. I just wanted to finish up this whole thing right here. All right. So now let's compare sort of I'm going to I'm going to rip an example straight from the PowerPoint, but let's compare propane. If we're doing radical chlorination of propane versus radical bromination of propane. So again, like we said before, bromine is going to care where it puts its radical. It's going to care where it touches down. So the bromine is going to make far more of the more substituted product, like 99%, versus 1% of the less substituted product. Whereas again, the chlorination doesn't really care too much. We could get various amounts of this one, like 50% of this one, to 50% of this one. Oops, there we go. 50% of this one. So you can see here that because chlorination is so unselective, it's so fast, it's not really going to care which one it makes. That is why a lot of the times you're going to see bromination used far more than chlorination because we can control bromination much easier than chlorination. All right? So let's compare this very quickly. Uh, Somebody said, but you can use it when there's only one type of hydrogen. Yes. So, like for example, if I had something like this, I could use chlorination because there's only one. Oh well. let's say that this just has like a bunch of fluorines around it or something. I could use chlorination with this and only make one product because there is only one group of hydrogens. Okay? Um, all right. So let's talk a little bit about that. Somebody said it doesn't prefer the more substitute at all. I think the book said 60-40. So we're actually going to do that very, very quickly because it does sometimes prefer the more substituted one. If worst comes to worse, what you should do is you should assume that the more substituted one will be the more, so this will be around 75, this will be around 25. It's pretty safe to assume that if you have a choice, if you have to make a choice, the more substituted one will be the more prevalent one. But what's important here is that you can see that bromine will make like 100% of this product. Oh, that should be bromine, not chlorine. And 0% of this product. Again, bromination offers way, way, way more control than chlorination, which is why we tend to prefer it over chlorination. And will you explain the mechanism using NBS? The mechanism is basically going to be the exact same if we use NBS over BR. So like if I put NBS here, that's not going to change anything except for the initiation step. The initiation step is going to be slightly different because when we do initiation, we'll again have light or heat, just et cetera, et cetera. And ooh, let's see if I can remember let's see if I can remember the structure off the top of my head. I think it looks like this, something like this. But what'll happen is we will essentially give off light, give it light, give it heat, and it will break this bond open and it will create one Br radical. And you may be wondering, well, what's the point then if it's going to do the exact same thing as Br2? Well, Br2 is not good for breathing in. NBS is also not great to breathe in, but it doesn't corrode your lungs like Br2 does. So that's why you may see NBS used more than Br2, just because it won't kill you as quickly. Um, so Br2 or NBS can also be used for allylic radicals. We'll get there. We'll get there in a second. I just wanted to sort of show this off for a second, but it's gonna be basically the same thing. It also controls the amount of Br added because again, Br2, the gas, gives off a lot of bromine radicals. Again, kills you faster than NBS. You'll learn all about this in organic chemistry lab if you're taking that next semester. Hopefully not online, but they tell you all about that, how bromine gas will be not good to breathe in. All right. So let's quickly talk about allylic radicals and all of those types of reactions. So let's say that we have this. Let me do my. Let's do this one here. So let's say we have this guy right here. Again, we went over this earlier, how we can have one of two radicals or allylic radicals, and we said this one here with this transition or this resonance structure, not transition state. I've been saying transition state too much. Is going to be more stable than the other option. Just to reiterate that. Okay. So let's say that we create our bromine radical. We create our bromine radical. It reacted with this guy to make HBr, and now we have another bromine radical that's going to want to react. And you say, oh, which one of these is going to be major? Well, both of them are going to be major. Remember that when we talk about these resonance structures, they don't exactly exist as separate resonance structures. They exist more as sort of a hybrid. So we have like kind of a double bond here, kind of like a half radical here and a half radical here. So it's just sort of like a 50-50 shot which one of these radicals the Br picks. So that means we will end up with two separate products. One that looks like this and one that looks like this. Exactly. This is Schrodinger's radical because we don't know what form it is in because it's not in either one of the forms until we react with it. Okay? So you can see here that when we have allylic radicals, when we have an allylic radical, we will end up with two major products. Okay? Does that all make sense? Whereas like very a very minor product would be something like this. All right. Is that a Br2 Hb reaction? This could be either Br2 HV. This could be NBS ROOR. It's just a radical bromination. In this case, we would get two major products, but four products overall. Yes, we would get four products overall, but I wouldn't worry about drawing every single one of the products because you could get like a question that looks like this, and then it's like, all right, show me the major products, and then you wait and draw all of the products, and then oops, you're out of time for the test. So most of the time, you're going to be choosing the most stable ones to draw. Okay? Does that make sense to everybody?
Casey,
Yeah, go ahead.
this might sound really like a dumb question, but with NBS versus NBS ROR, what would be like the difference? I guess like I know NBS always has to like is it always with the allylic radicals?
It's so that is confusing. Like it looks like it's gonna always be with allylic radicals because that's how it's drawn in all of the questions on the lecture. But it can be done with other things basically.
Okay, all right, thank you.
Yes, a lot of the times when we do these allylic reactions, again, you can do it Br2, and NBS isn't really used, or I'm sorry, NBS is used more than Br2 just because if we have Br2 and HV, we could like very, very possibly like a small chance do the addition reaction with Br2. But I mean, it's it it's such a small amount. I would say you could use both of these for the radical reaction. Okay? Somebody said the one on the right is preferred. Neither one of these is technically preferred, but yes, this one is created from the more stable radical. Okay? All right. Somebody asks, would using NBS ROR add Anti-Markovnikov? And funny you should ask that. We're just about to get into that. So what you're asking about is radical addition versus ionic addition. NBS and ROOR, that would not really be used for radical addition. Usually we'll use something like HBr with HB light or ROOR in order to do that radical addition because NBS doesn't really give off any hydrogens. Somebody said, so you have to narrow it down to the more stabilized or the more stable allylic radical and then make products form from those resonance stabilized possibilities. Yes. So just to reiterate, both of these products will form relatively equally. Technically, this one on the right is formed from the more stable radical, but the thing is neither of these radicals, again, neither of them exist exclusively because they exist as a hybrid structure. What that means is we could have one or the other and we wouldn't know until we actually react it. So that means we have both of these radicals, or both not radicals, but both of these alkyl halides as final products, as final major products, because they're both from the more stable allylic radical. Okay? Does that make sense? All right. Okay, so now we're going to talk about, oops, I just knocked my little microphone thingy. Now we're going to talk about radical addition versus ionic addition. So first off, when we talked about ionic addition, remember we started with HBr, and we just did this mechanism right here. I know this probably feels like it was forever ago. And you're like, wow, I don't remember this at all. And that's okay, because I'm here to remind you. So remember, when we formed this guy here, we formed a carbocation intermediate. Okay? And so let's pause here really, really quickly and let's compare this to our radical reaction, our radical addition. So what happens in radical addition, essentially, is we are going to start off with HBr with something like ROOR or whatever. Usually it'll be ROOR because what's going to happen is first these are going to form into two radicals. But I'm just going to show what them separately right here and right here. And so then one of them is going to react with this hydrogen, create a new bond with it, and then break that bromine bond, bromine here, and then that creates our bromine radical plus HOR. And so then what occurs is that this bromine is what reacts first. So if we look at ionic addition, the hydrogen reacts first. So now we're going to have the bromine react first. So if we react that bromine with the same sort of the same double bond here, what will happen is it's going to create a radical from that double bond. And what this means is that it's going to want to form the more stable radical. Thus, it's going to add to the same place that the hydrogen did when we did ionic addition. Okay? All right, and so then when we end out ionic addition, what happens is the bromine attacks that positive carbon, and we end up with Markovnikov addition. However, to finish out the radical reaction, our HOR is basically going to get stolen by this radical right here, and we end up with our final addition product, which looks like this. And this is anti-Markovnikov. So you can see here that when we added Markovnikov, the hydrogen was added first, which we can see sort of forced the carbocation to go onto the more substituted carbon. Whereas when we did radical addition, our bromine added first, which forced the radical to go on the more substituted carbon. So we can see here that the order that these substituents were added in sort of defined whether or not it's going to be Markovnikov or anti-Markovnikov. All right? Does that clear up any questions you may have had about this? In this mechanism, why does adding the Br take away the double bond? Well, the thing is you can either create an allylic radical. So the thing is you can either create an allylic radical right here, and then that takes up the Br, and then all we're left with is this HOR, which would then add its hydrogen back, which would then just put us back to square one. So the reason why it doesn't make an allylic sort of structure like we saw before is because there would be no point to it. Remember, we made it allylic when we were adding bromine, but here we're adding bromine and hydrogen. So HBr will always have an ROR. I hate saying always and never in organic chemistry, but it's a safe bet to say most of the time you're going to see ROOR. Yeah, HBr will not react alone and create an anti-Markovnikov structure. When it reacts alone with a double bond, it will create the Markovnikov structure. All right? Okay. So I think that's it, and up to the free radical polymerization. So does anybody have any so why with HBr and ORR it will add to a tertiary first if available? I don't think I understand your question here. So, like for example, like I said before, we will not add or we will not take away hydrogen from this carbon structure because the next step is to add a hydrogen. So if we take away a hydrogen and we just add that same hydrogen back again, then there would be no point and we just end up back at our starting place. So that's why it sort of forces the bromine to add to the double bond rather than making a radical. Does that answer your question? Okay, awesome. So are there any more questions. And don't say sorry for asking questions. I'd rather you ask than just sit there and wonder if you're right or wrong. All right. Then I will clear this. And then we will talk about polymerization, and then we'll be done with Module 10. All right. So the idea of polymerization is the idea of sort of unfolding double bonds in order to create a new very long strain, a very long polymer. So let's say that we have this guy right here. For the polymerization, what will happen is we initiate this. We'll initiate this with light heat, but more often than not, we'll be initiating it using ROOR, which of course we know will create these RO radicals, which will then essentially add to this double bond. And again, it's going to add Anti-Markovnikov, and so we end up with something that looks like this. Okay? And then we can see that if we react this with another one of those monomers, it will react in much a similar way to this RO group. It will add to the radical in a way that puts the new radical on a more stable carbon. So that means that this will become, let me see if I can draw this correctly. Sorry, I always have trouble sort of unfolding these at the very beginning. Yeah, okay, I see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So we have RO over here, one here and here, and then it'll just keep going on and on. And the way that I always sort of figured these out is I would take my beginning monomer and I would highlight that double bond in red. Then I would say, okay, so this double bond is attached to two carbons, one here and one here. When I create my polymer, this double bond is going to sort of reach out of those carbons there. It'll break apart and it'll reach out on either side. So what I'll see here is I'll see, okay, here's a new bond right here. Here's a new bond right here. Here's a new bond right. So like every other bond is from that beginning double bond. Let me make this a little bit clearer with an example from the PowerPoint where we have this here, where we have Z. So we know we have Z here. Here is our double bond right here. It's attached to these two carbons. So when we break that double bond, it's going to unfold outwards from these two carbons. So that means we're going to have 1, 2, 3, 4. So 1, 2, 3, 4. Here is the double bond unfolded. Here's where the double bond used to be. And we know that Z is going to be right here. And so then we keep repeating this. So we say, okay, so it's attaching to another place where the double bond used to be, which is then attached to where the double bond used to be. So you can see here we're sort of alternating. Pink, blue, pink, blue, pink, blue, because every other bond is a new bond from that double bond sort of unfolding outwards. All right? Does that make sense? Does anybody have any questions about that? I'm going to do another example in a second, but I just want to make sure everybody is sort of on the same page here, because this is sort of a kind of a difficult topic. Will you give us practice problems at the end? I will do my best. These practice problems are significantly harder to do than SN1, SN2, E1, E2. How did you count it again? So let's do another example because I feel like doing examples is the best way to learn this. So let's say that we have this guy right here. All right. So the first thing I'm going to do is I'm going to highlight that double bond. So my double bond is right here. And I can see my double bond is attached to this carbon and it's attached to this carbon. So I know when I unfold that double bond, I'm going to have a linkage here and a linkage here. So that means that I'm going to have 1, 2, 3, 4 sort of linkages keeping my polymer together. So I'm just going to draw 1, 2, 3, 4. So I can say I'm just redrawing what I've drawn right here to have my blue lines here and have my previous pink double bond right there. And I know on the left side of my double bond, right here, I'm going to have 2 methyl groups. And on my right side, I'm going to have 1 methyl group. All right, awesome. So now I'm just going to do that again. So 1, 2, 3, 4. I'm going to say, all right, so after a blue, there's always going to be a pink. That is not pink, that is red. There's going to be a pink. And after every pink, there's going to be a blue. After every blue, there's going to be a pink, and so on. And pink is where our sort of base carbon is. Our 2 base carbons are. So that means that on this carbon right here, there's going to be 2 methyls. This carbon right here, there's going to be 1. 2 methyls, 1. And then so on and so on. Okay? So a double bond results in 2 new carbons. A double bond results in 2 new carbon bonds. Sort of think of it as sort of like a drawbridge, sort of opening up and out in order to connect to other carbons. Think of it as you have 2 arms. You can think of it as when you hold your arms out linked in front of you, there's only one sort of continuous arm here. But when you open your arms to hold hands with other people, then you have 2 new connections. Okay? So this continuously repeats exactly. All right? Does this make sense to everybody? Does this sort of clear up questions you had about? Again, you can think of it as oh, this monomer I kind of made up on my own. So it's like again, you're like a little person. You're sad because you have no friends because you're holding your own arms because that's your double bond. But then what you do is you cut your arm in half. And you're nice and happy now because you could hold your arms out to other people and make 2 new connections. Oh, somebody asked a question that I did not see. So what is the monomer? Oh, this monomer here, I just kind of made it up. This isn't something that that is real. I just kind of made it up and turned it into my monomer. Essentially, anything with a double bond can turn into a monomer. There's just no specific name for this one. Okay, does that clear that up for you? Okay, awesome. Okay, so let's say that I give you let's say that I give you some sort of polymer. I'm going to give you this polymer and I'm going to say, all right, so this has chlorine and this one is going to have, I don't know, this here. And then chlorine and this here. Okay? So we can see here, obviously there's going to be some sort of repeat pattern here. And I'm going to say, all right, so if I say here is one arm, here is another arm. Here is one arm, here's another arm. Wow, this guy has like a really tall neck, I guess. So every other arm is going to have a different color that I'm going to label it with. So this one's going to be pink, 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 pink. Okay? And so then the other ones I'm going to label as blue. So it's going to be blue, 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 blue. And I'm going to say, all right, my pinks are going to be where my original bond used to be. All right? So we can see that we said the pinks are going to be where our original bond used to be. So the pinks are kind of like holding the heads. So like, uh-oh, this is going to look really freaky. Here's our head right here. Here are our heads right here. So one side of the arm is holding the head, and then the other side is going to be holding the chlorine. Okay? And so we can see that when we get rid of this bond right here and we bring this back together, we get rid of this right here, we get rid of this right here, and we put our double bond right here, we can see that our monomer looked like this. And we see that here, we can see that our monomer. Sorry, this looks really creepy, but I'm trying to keep the analogy going. We can see that that's sort of the same way here. Does this make sense to everybody? This analogy sort of breaks down in a little bit, but hopefully it's just creepy enough to make you remember it. Feeling more lost? Okay, so yes, it's essentially just putting these drawbridges back down. We take this and we put them back down. Like the drawbridge example? Yeah, I do my best to make as many metaphoric examples as I can, but it gets kind of crazy when you get into the polymers here. But essentially what we're doing here when we had this, we took in the drawbridges and just made them into a new double bond. Somebody said, so essentially he'll give us a monomer or a polymer and ask us what the monomer or the polymer is from the starting compound. Exactly. All right, does this sort of help you understand polymers and monomers and how everything comes together? Do you mind doing another example? No, I do not. Let's just do one more example without the creepy heads. Sorry about that. My metaphor ran away without me, I guess. So we'll have this. We'll have these here and these here. So we're gonna say, all right, every other leg, just to make sure the monomer will always have the double bond. Yes. We'll make every other leg pink. So pink, pink, pink. And every other leg will be blue. Blue, blue. And we're going to say, all right, so the pink is going to be our legs going outward. And we can tell that there are legs going outward because they're pointing outwards from the squiggly lines. So that means that our blue is going to be where our beginning double bond was. So what we're going to do, we're going to close the drawbridge. Here's our blue here. Let me change. So here's our blue. We close the pink drawbridge, which is right here. Back to this here. We close the drawbridge. And so on the one side, we're going to have, or on the left side, we're going to have 2 methyl groups. And on the right side, we're going to have 1 ethyl group. All right. Does this make sense to everybody? Does this maybe clear this up? Okay, awesome. Sorry for that creepy metaphor. I just ran with it. All right, awesome. So I think overall we are done with chapter 10. And then we will get into chapter 11, which is everybody's favorite synthesis. All right, so just to explain this bridging thing one more time, essentially what I did is I sort of circled around this guy right here. I circled around here and I redrew him like this. And I said, all right, so here is my blue bond. Here's my blue bond right here.
Mm-hmm.
And when I sort of close these drawbridges, I'm going to close the bond from this side. I'm going to close the bond from this side, and then they'll come together to make a new double bond right here.
Oh, I see it now. Okay,
Yes.
cool.
Okay, awesome.
Wait, that actually makes so much sense.
Yeah. Okay, awesome. Sorry, I guess my horrifying person example didn't hit the mark that time. All right, so now we're going to talk about synthesis. So synthesis is sort of it's not a difficult concept to get your head around. It's more difficult to put it in practice without messing up all the time. But it's okay to mess up, especially with me. Because if you mess up with me, I'm not going to flail you alive or draw and quarter you. Like, how dare you mess up this synthesis? No, getting things wrong is part of the learning process. So don't worry about getting things wrong, at least not with me. Okay? So there are a few things to think about when we're talking about synthesis. First, we have to compare the reactant. I'm going to put reactant versus product. And when we compare the reactant versus product, we have to see, does the number of carbons change? We also have to say, do pi bonds change? Like, do double or triple bonds change? Okay. We also have to look at the reactant. Just as a reactant, we just say, all right, what reactant is it? And what can we do with that reactant? So like what reactions will the reactant do? And then finally, we'll look at our product. And our product, we have to say, okay, so what is our product? And what reactions lead to product? Okay? So if we sort of take this into account, let's quickly do something like this. We say we go from this to 1, 2, 3, 1, 2, 3. We go from that to this, and I say, how did we do that? Well, you would say, okay, first off, our reactant, that is an alkyne. That's a terminal alkyne. We know terminal alkynes can create acetylide ions if we need more carbons, and it can also we can also add halogen. We can do halogenation. We can do hydrohalogenation, and we can make a ketone with it by doing our hydration using an acid, or we can make an aldehyde with it using hydroboration oxidation. And then we go over here. Okay, here's our product. This is an aldehyde. We can create an aldehyde through the hydroboration oxidation of triple bonds. I don't think we know of any other way right now as far as like what reactions we know, because there are other reactions that will make an aldehyde, but I don't think that we've gone over them yet. So HB means hydroboration oxidation. I'm using like really shorthand. But again, I don't think we know of any other reaction that will give us an aldehyde. That we're using Lindlar's catalyst or zonolysis. Oh, okay, so we can also use zonolysis. And we're going to say, okay, so we start with 3 carbons. Oops. We start with 3 carbons. We end with 3 carbons. So that means we're not changing ozonolysis as far, it depends. We'll talk about ozonolysis. So if we had ozonolysis like this, like for example, if we had this guy right here, and we cut him in half with ozonolysis, all we do is we're going to replace the double bond with oxygens, which then will make aldehydes. All right? But we would have to turn it into an alkene first in order to do that. But yes, ozonolysis technically will create an aldehyde. But what's also important to note here is that we start with the same number of carbons that we end with. So we will not be able to do ozonolysis, and we will not be able to create an acetylide ion. Why? Because both of those will change the number of carbons. All right? And we say, okay, we know this is an aldehyde. We know we're not going to be doing halogenation, hydrohalogenation, or making a ketone. So the only possibility for us is we're going to be doing hydroboration oxidation. Okay? Does it make sense how I sort of broke this down and sort of showed you how to, I don't know, for like a relatively simple problem, sort of see how you would sort of walk through this yourself? Does that make sense?
Yeah, it's nice that you like showed us like steps on how to approach it, because I'll look at it and I kind of get overwhelmed because I know that there could potentially be like more than one correct way to get to it. So it's nice to like look at it in steps.
Right. And you don't have to write all of this out. Like immediately I saw, oh, I can make an aldehyde with an alkyne. I know I'm making an aldehyde here. I can just do that. I did not have to go through like this whole thing. We're talking about ozonolysis, blah, blah, blah. But this is a really good method when you're first starting out. Because I know you're probably not going to because like ozonolysis, yes, it's different with alkenes because overall, when we're looking at this aldehyde, we're not looking at it in relation to the reactant. We're listing off ways that we can make it. Because remember, when we're doing synthesis, this can be done in multiple steps. We are not limited to doing just a single step. Like, for example, this one is definitely a single step. But if we did think about it, we could say, oh, we can do ozonolysis with alkenes in order to make an aldehyde. That could possibly be an answer for another type of question. It's just when we're looking at the products and looking at the reactants, first we're going to look at them separately to see how do I get to the product, and how do I go from the reactant and see if there's any type of overlap. All right, does that make sense? So we can see here that obviously we're going to have to do hydroboration oxidation. So what this means is we're going to have to do Hbr2 for step 1, and then step 2, H2O2 and OH negative. And then that is going to be the synthesis for this one-step problem. All right? Does that make sense to everybody? Okay, so let's do something similar. Oh, go ahead.
Sorry.
No, you're
I
fine.
think he'll ask us to show the mechanism too, like, because a few homework problems have like all like the steps and they want us to know.
So, as far as drawing the mechanism goes, again, these tests online, they're either multiple choice or fill in the blank. So it's very hard to sort of test on can you draw the mechanism. Yeah, you could write it R2BH as well, but oh my goodness. One more thing. Sorry, a lot of people are asking me questions. So again, if he asks you about the mechanism, I think the most he could probably ask you is select the proper mechanism from the choices below. And yes, you should know all of the previous mechanisms from this class. I can hear your defeated groans and sighs from here, but it is important to know. Somebody said, I thought hydroboration oxidation added an OH. Is it still OH, but the hydrogen is not pictured? All right, so let's review. Whenever we do hydroboration oxidation with a terminal alkyne, what we're going to end up with is 1, 2, 3. Oh, 1, 2, 3. We are going to end up with, yes, we're going to end up with an oxygen right here, but a double bond right here. Remember, this is an enol. And whenever we have an enol, it'll undergo tautomerization and become that aldehyde. All right? Somebody said, if he asks us to count step, is this 1 or 2 steps? Because hydroboration itself isn't 1 step. I would say this would be 2 steps. Like this would be a 2-step equation because you start with Hbr2 and you then go into H2O2 and OH negative. I would say this is 2 steps. Okay. I know probably on your homework it lists it together as 1 step, but if it doesn't list it together on the test, then just assume that they're separate steps. Why Hbr2 instead of Bh3? The only reason why I'm using Br2 versus Bh3 is just because Hbr2 is a lot more stable when it comes to alkynes. That's why when you see us reacting with bromination or boronation, hydroboration oxidation with an alkyne, a lot of the times we're going to see Hbr2 just because it's more stable. It's less likely to overreact with that alkyne. Okay? Does that make sense? Okay, awesome. All right. Okay, so let me erase this and we're going to do one. Let's expand on this very quickly. Oops, I just moved my screen. Did not mean to do this. Let's erase this and let's do the same reactant, but we're going to try and make a different product. And we're going to go through the same exact process as we did before, but now I'm going to warn you, this is going to be more than 1 step. So we start with this. Oh dear, I started my camera. Sorry about that. Fat fingers. So we're going to start with this, and we are going to end with 1, 2, 3, 4. We'll end with this here. Yeah? Yeah, that works. Okay? So we're going to see here immediately, we're going to say, okay, here's our reactant. Again, it's an alkyne. It's a terminal alkyne, so we can do acetylide ion. We can do hydrohalogenation. We can do halogenation. We can do hydration using an acid. We can do hydroboration oxidation. Is there any that I'm forgetting? Oh, we can. I think that's it. Off the top of my head, that's all I can really remember. So you can say here, okay. Now what do we have here? We have a ketone. Sorry. So there are a few ways that we can form a ketone. We can do We can do hydration using an acid of an alkyne. We can again do a zonolysis. And I think that's most of the ways. I think those are the only two real ways that we know of to create a ketone, because we haven't gotten to oxidation or reduction yet. All right? And so what we'll do here, we'll say, okay, now let's count the carbons. We start with 3 carbons over here. We end with 1, 2, 3, 4, 5 carbons over here. So what this means is that we grew our carbon chain by 2. The only way we know of to grow our carbon chain is to use the acetylide ion and add an alkyl halide. All right? So we know first off, okay, we're going to have to do some sort of acetylide ion. And then we say, okay, so this is a ketone. We know we can do a ketone of the hydration of an alkyne or a zonolysis. But for our case, oh, my battery's running low. Let me plug it in. Sorry. For our case, the hydration of the alkyne is going to be way easier than trying to do a zonolysis. Why? Because we start with an alkyne. So that means that for this, we're definitely going to do the acetylide ion to grow our carbon chain, and we're also going to do hydration using an acid. And so now we're going to think to ourselves, okay, what order do we have to do this in? Because the order is important. So let's think about this really quickly. If we go ahead and make the ketone first, there's no way for us to do the acetylide ion, because when we make the ketone, we get rid of the triple bond, and there's no way for us to do an acetylide ion. So that means that we have to do the acetylide ion first. So that means we are going to use a strong base, NaH. So that'll be step 1. And we will make our acetylide ion. And then what do we do? Well, we're going to want to grow our carbon chain by 2. So we're going to use an alkyl halide that has 2 carbons that will be attached to the halogen. And of course, we're going to do an SN2 reaction. So this will be step 2. And we end up with 1, 2, 3, 4, 5, like this. And then finally, we're going to do our hydration using an acid. H2SO4, H2O, HgSO4, which will make the enol. So let me draw it over here. So 1, 2, 3, 4, 5. And we know that we have 1, 2. So 1, 2. Here's a double bond. Here's our OH, which then will tautomerize. So I'm going to taut here into our ketone. All right. So you can see here, overall, we're using 3 different steps because the tautomerization just sort of happens spontaneously. So we don't generally count that as a step. All right. Okay. So, and yes, Brandon, you're 100% right. Does this all make sense to everybody? Do you see how we got from step 1 to step 2 to step 3 to the final product?
I have a question real quick.
Oh, go ahead.
On the book, it always uses like a sodium ion, but can it be a chloride ion as well to add on the carbons?
Like, do you mean it looks like this?
Yeah.
Dr. Dowdy tends to use the alkyl halide or with the chlorine or the bromine rather than this. I'm not sure where the book gets this from because it would be slightly different if we have something like this.
Okay, thank you.
Okay.
I have a quick question real quick.
Go ahead.
The acetylide ion, why would that not be like included in this? Like, I know like in the book it said like, oh wait.
You mean this right here? Oh, sorry. You mean
Which
this
one?
right here?
Yeah, never mind. I figured it out.
Okay, all
Sorry.
good. No, you're fine. Why did you use hydration instead of a zonolysis? Because hydration, way easier. Because when we hydrate an alkyne, we will make a ketone. We already have an alkyne, so why would we go through so many extra steps to try and create an alkene that when we cleave will create the correct ketone? It's just way, way easier because, again, a zonolysis of an alkyne makes a carboxylic acid. Yes, you're correct. Which means that we'd have to transfer this into an alkene before we can do a zonolysis. And we have to ensure that when we cleave that alkene, we're only going to get this product, which is why it's leagues easier to just do the hydration rather than a zonolysis. Okay? Does that make sense? Why we did a zonolysis, or why we did not do a zonolysis? Because hydration is just way easier, way less steps. And the less steps, the better, because we're super lazy in this class. All right. Does anybody have any other questions about this? Did I help you kind of understand synthesis a little bit better? Well, he said the max would be 3 to 5 sets. Yeah, definitely. Okay. So one thing I want to touch on very, very quickly is I'm going to clear this. We're going to write P here. Oops, we're going to do it in pink. Whenever you're starting with like a regular alkane that looks like this, if you're starting from this and you're going to some sort of crazy product or whatever, that I just made this up really, really quickly. But whenever you're starting with an alkyne, I mean not an alkyne, but an alkane, there's a very, very, very good chance that you're going to be doing a radical reaction first. Because remember, the radical reaction is basically the only one that we know that will react with regular alkanes. Okay? I'm trying to think of any other fun little tidbits, fun little tidbits of advice that I've picked up. But always go for the yeah, no, I'm definitely gonna go over retrosynthesis. I'm just trying to think if there's any other little pieces of advice and patterns that I picked up. Again, there's probably 15 different ways to do the same exact synthesis, but 99% of the time you're gonna want to do uh, the the easiest and shortest synthesis possible. So a lot of the times you guys are gonna work way harder than you have to, and then it's gonna be like, oh, by the way, this could have been done in 2 steps. And yes, sometimes you're going to want to prefer certain reactions that take a billion steps because that would be quote unquote green chemistry. But again, in this class, everything that we're doing is sort of on paper. We're not actually in the lab doing these reactions. The idea behind green chemistry is going to be more for when you actually go into a lab and you start doing reactions yourself, you start plotting out these mechanisms yourself. Again, in this class, green chemistry on paper, where we're trying to do mechanisms, isn't going to be a big factor. You should just know what green chemistry is and maybe an example of green chemistry versus non-green chemistry. Like, for example, if you remember way back in when we were talking about alkenes, whenever we do syn dihydroxylation or epoxidation or whatever, we'll be using stuff like KMNO4, which is pretty bad for the environment. So there was an alternative method, which was the catalytic osmium, where you have OS 8 plus, I think. It's either 8 plus or 6 plus, which then is used to sort of reduce the or oxidize. Oxidation is loss reduction. Yeah, no, it reduces that double bond without giving off bad byproducts, which is why this osmium would be considered green energy over KMNO4. But again, in this class, we don't worry about it too much because we aren't actually in the lab. We're doing all of this on paper. Yeah, I'm trying to pollute the earth, trying to make global warming go faster. But anyways, so, retrosynthetic analysis. So now that we've talked to you synthesis, I'm going to make it a little bit harder for you. In some ways, this might make it easier. So, like for example, let's say that I give you, this is straight from straight from the PowerPoint. Let's say I give you this here, and I give you this weird looking arrow here. This open arrow, what that basically means this will be the product and this will be the reactant. You're going to do the exact same things that you did before. Like, how do we make this product? Well, to make an alkyne, we know we have to do elimination twice of a geminal or a vicinal dihalide. And this is our reactant. We know our reactant it can undergo dehydration. It can undergo some reactions that we haven't talked about yet, so we're not worrying about it yet. I think dehydration is the only one that we've really talked about this in this class. Okay? Again, retrosynthetic analysis versus forward analysis, it's all up to personal preference. Some people find it easier to go backwards. Some people find it easier to go forwards. Like, for example, some people say, oh, well, I know I need either a geminal or a vicinal dihalide. So if I want to go backwards from this, I know I need to make either a geminal or a vicinal dihalide. And I'm just going to make a vicinal one because I remember my best TA Casey ever saying a geminal dihalide comes from an alkyne already. So most of the time to generate an alkyne, you're going to be using a vicinal dihalide. And so then you say, oh, I know I can make a vicinal dihalide. How do I do that? Oh, I remember if I do a halogenation of an alkene. Oh, wow, there's my alkene. Oh, how do I make an alkene? Oh, I can dehydrate an alcohol. Okay? Again, going backwards versus going forwards, that is all up to you unless a specific question asks for it. But I think as long as you get the correct answer, like if you get the correct mechanisms, the correct order of the reagents, I don't think it should matter too much. All right? Does anybody have any questions about this? I mean, honestly, that's most of synthesis. There's not a lot going on with synthesis because basically all you have to do is sort of apply everything that you've learned up to this point. Okay? Does anybody have any questions? All right. So it just came to my attention that we have not actually gone over dehydration yet. So I wouldn't worry about it too much for this step. Like if you did not know what dehydration was, don't worry about it because we haven't gone over that yet. That is chapter 12. So a lot of the times you will not, most of the time, I don't think you should be seeing stuff like this, like with dehydration and everything. Somebody, oh, go ahead.
Sorry, they did use what do you call it? Concentrated H2SO4 to dehydrate.
Yeah, just as a quick lesson, I guess. To dehydrate, basically you're going to use an acid plus heat. Because essentially what that does, that's going to turn OH into a good leaving group and do sort of an elimination reaction following that. But I wouldn't know it too well because again, we haven't actually gone over it yet, which is fun. So I don't think he would ask you something like this on the test, just because we have not gone over any of that mechanism yet. Okay? Sorry about that, guys. Usually, again, just as a heads up, we changed books this semester, so it's in a different order than I remember. So you would have covered dehydration by now, if we were using the same book. And yes, it does have a very similar function to TS. What TS does, it replaces this hydrogen and turns into OTS, which is a good leaving group, and then we deprotonate and turn this into another elimination reaction. Again, this is something that I don't think that we've gone over yet, so I wouldn't worry about it too much. Okay? Does that make sense? Does that answer your question about that? Okay, awesome. All right, so I think I covered everything in that list. Is there anything that you guys noticed that I missed that I didn't mention? So this question, for this question we would use For this question, our order of reagents would first start with dehydration. So one, we would start with like H2SO4 plus heat. H2SO4, H2O, and heat. Again, reagents you don't know yet. Followed by Cl2, followed by elimination twice, which would essentially be, well, let's just use, I'm trying to think of one off the top of my head. Let's use tert butoxy. So we'll use this to do elimination, and then we end up with our final product. Okay? All right. All right, so that's about the end for this review. I'm sorry I couldn't do more practice problems, but I have another meeting to go to. But so everyone, good luck on your test, and let me know if you have any additional problems. I'll be happy to help if you message me on GroupMe, through email, through Discord, whatever. I'm happy to help. All right. So have a great rest of your day. Good luck on your test.